Don't worry. I think it's for
Okay.
me, it would be I'm just bothered about people seeing it, but you don't see
No,
anything.
no, we
Okay.
don't. We just see your slides and your pointers.
Mm-hmm.
You can even use it to point.
Okay. Yeah, the pointer, that's great. All right.
Okay, thank you, Stephanie.
Okay, so then I'll start in that case. Okay, so thank you so much for the invitation. I'm also very honored to be speaking at this series, and I've actually followed the series with really excitement. I think it's so great that you're doing that, and you attract an amazing list of speakers so far. So I feel really honored being asked as well.
Thank you so much.
Okay, so yeah, in this talk, I'm going to present actually some recent work that I did jointly with Farsane Derakhshan and Limin Jha. Farsane is just started a postdoc with me, so I'm really very excited about that, and we continue that kind of work. So in this work that I'm presenting, we kind of laid hopefully the foundations for moving forward. All right, but okay, now I have this issue again with my slides. Okay, so I have to use my mouse pointer. Sometimes Zoom kind of screws up Keynote. I don't know why, but anyway, so I was able to advance the slide. So let me just briefly provide some context. So Clément has already mentioned that I did quite some work on concurrency and also using logic and type systems. And more recently, I used what I'm referring to as possible worlds type systems. So here the idea is basically that we enrich the typing judgment with possible worlds from hybrid logic. And then we kind of impose constraints using those worlds on the typing judgment and the derivation to ensure properties of interest that we want to verify then by type checking. So to give you a few examples, in the past, I used this approach to make sure that shared session types, which are an extension of linear session types that actually support a form of safe aliasing, that they are deadlock free. So I used the possible worlds idea in that setting. Then some ongoing work that I haven't finished yet is on disentanglement. So disentanglement is a property, a memory property in parallel programs. So ML with references. And essentially when this memory property holds, you can use a parallel garbage collector and it's all safe. So you're not reclaiming something too early. And in this talk, I would like to talk about the most recent work, where we use this possible world type system to ensure non-interference for a session typed language. All right. So the idea is basically that we use possible worlds in a type system, so actually a linear session type system, to enforce or to establish some kind of information flow control. I would like to highlight that the work that I'm presenting is deeply rooted in intuitionistic linear logic session types. So I'm really making use of the fact how the heap or the program configuration is structured at runtime because of intuitionism. Basically, in order to prove that the information flow control system that we've developed ensures the property that we are after, that is non-interference, we developed a session logical relation, which is really a generalization of existing logical relations for session types. So logical relation have like a rich history in like functional languages, and then more recently also in the context of Iris and possible worlds, also like Amal Ahmed's work there. But these were all like for more imperative programs. And here we had to adjust the work that existed, which was primarily used for non-termination and also parametricity argument, in order to use it for non-interference. In case I was able to spark your interest in this talk, I would like to mention that we have a paper on this. It's on my website. It has been presented at LIC, so it will be also available on DBLP. And we have also a technical report that I link to on my website. All right. I'm not assuming that people are generally familiar with information flow control and non-interference, so I'm trying to provide some intuitive introduction. So what is information flow and non-interference about? Well, at the end of the day, the property that we want to prove is basically that we want to protect the confidentiality of data that are in our programs or our programs deal with. And as you might guess, the most immediate concern is to make sure that we kind of make sure that only authorized users can access confidential data. But an even more important concern, or let's maybe not say important, but less immediate concern at first, is that also should entail how secure information or confidential information propagates through the system. So even if we make sure that only authorized people can access data, it may actually happen that some user propagates advertently or on purpose confidential data to someone who should not have access to it. So that means that we have to impose some mechanisms, static or dynamic, that allow us to control how information or secure data flows through that program. And the verifiable property that we are after at the end of the day is referred to as non-interference. Very simply put, non-interference ensures that an attacker cannot infer any secrets from just observing how the program behaves. And of course, that notion of non-interference has to be kind of formally stated, and also has to be worked out for a particular programming system that we're looking at, and also like the paradigm that we're using. And I will say more about this later. Okay, so to warm up, let's look at an example. So, well, very natural, at least for me, because I'm Swiss, is to look at a banking example. So we have a bank, we have two customers that have accounts with that bank, which are Alice and Bob. And in addition, we have like walk-in customers who just enter the bank and might want to ask the current interest rate or whatever. So typically in a security setting, in order to ensure that everything's safe, we establish we basically expect the system here in this example that Alice can only access her account, and also the bank can access Alice's bank account, but it shouldn't be possible for Bob to access Alice's bank account. And similarly, also for Bob, we do not want Alice to be able to access his account, or just a walk-in guest. In order to basically, now the challenge is now that there could be possibly an attacker disguised as a guest, right? So we have to kind of make sure that our system at the end of the day is safe, which kind of forces us to define what are the different levels of confidentiality there exists, and how they are kind of relatively ordered with each other. So this is typically done introducing or defining a security lattice for the application that we are considering. And as you can see that for our example, we probably would set up the lattice where we have the labels bank, Alice, Bob, and guest. And we order them such that bank has the top security clearance. So anything that has level bank is allowed to know anything or everything. And Alice and Bob, on the other hand, have a higher security clearance than the level guest. But what is important, because we have here a lattice, it's possible that two labels are not directly related with each other. So here, for example, Alice and Bob are not. So Alice nor Bob, they cannot access each other's information. All right, so this security lattice basically defines who is allowed to know what. All right, so keeping this security lattice in mind, let's look at our application and play with some programs here. I would like to point out that I'm taking here a message passing approach. So what does that mean at the end of the day? It means that computation happens in this context by the exchange of messages. So in particular here, I'm representing on the slide each actor or entity in this system as their own little icon. So I have a bank, I have Alice, I have Bob, I have A off to represent Alice authorization entity, and B off for Bob. And then we have the two bank accounts, which are actually protected by the authorization entity. And since it's message passing, I refer to those entities as processes. So they're basically computing and they're available in parallel. All right. So you might have already heard that session types are typically used in such settings to type the protocols that arise from message exchange in such systems. And I'm actually going to use that, and I'm going to define 3 session types. So I have auth for authorization, I have ACK for account, and cust for customer. I'm not going to require you to understand the details of this. I'm posting a legend at the bottom of the slide so you can see what the individual connectives mean. And those of you familiar with linear logic will notice that these are the connectives of intuitionistic linear logic. And that's basically the foundation of this kind of language that we are developing here. But just let me give you the intuition, what those session types, what kind of protocols they define. So let's briefly go through them one by one. So the first one I said describes the protocol of the authorization process. In particular, that means both Alice's authorization process and Bob's authorization process are governed or have to adhere to that protocol. So what does that protocol say? Well, it says, as a client, send me any of the tokens 1 to token n. And if you happen to send me the correct authorization token, I will respond to success with you, and afterwards I'll send you the channel to your account and I terminate. Otherwise, if you send me the wrong authorization token, I'll respond with fail and terminate afterwards. Okay, so what about the account? I'm keeping here very simplistic. So in particular, we're not supporting values. It's really like more in line with the original Pi calculus where we only pass channels. But of course, the system could be easily extended to support values. All right, so given that, how do I represent the protocol and session type that governs the protocol of an account? Well, again, I keep it simple. Basically, the account, when I query it, tells me whether its balance is high, medium, or low, and then it terminates. So what about the customer? Well, the customer expects to receive a channel that provides access to its authorization process, and then it terminates. Okay, any questions up to here?
Nothing on the chat.
Okay, good. All right, so then I'll. Good.
No, I think you're building up slowly, so that's perfect. I think that's
okay, good. Okay, excellent. I'm glad. So then now let's look at an example here. So I have just some code. There's of course some kind of setup code required, but I'm just jumping in and diving in and focus on the two most important code lines that we're looking at. So what are we doing in line 1? We're going to send Alice authorization process to Alice. And when we run that code, actually, we can now see that Alice received the channel that gives her access to her authorization process. And we can really represent that kind of graphically on the slide, where now everything moves under Alice. So I hope you can appreciate this, that this is a nice way to think about message passing protocols in a linear setting. All right, because here really what happened is an ownership transfer of the channel. Okay, so now let's look at the second line of code. Well, we do the same thing for Bob, right? We send the authorization process, the bank actually sends it to Bob. Well, I have a question now. Do you think that's a secure program? Well, what we did is we gave Alice access to her account and Bob access to his account. That's in line with the policy that we set up before. So that's a totally okay program. All right, let's look at a slightly different program. What about this program? Now in this program, we are going to send Bob's authorization process to Alice and Alice's authorization process to Bob. Well, this potentially provides access to, so Alice might get access to Bob's account and Bob's to Alice if they guess the authorization token correctly. So that's an insecure program, and it amounts to a so-called direct flow. All right, so let's look at another kind of flow that we can encounter in such programs. And for this, I'm going to change the program slightly. Now I'm going to replace Alice's authorization process with a sneaky authorization process, which behaves to Alice the same way. But in addition, this sneaky authorization process is also connected to a malicious intruder, and it's going to send messages to that intruder. So let's look at our program. That's now the program that is running on the sneaky authorization process. As you can see, it cases first on the authorization channel that it has to Alice. So, which means it will receive any authorization token from Alice. So let's assume right now Alice sends the correct authorization token. So what does it do next? Well, it's going to send the success message to Alice because she sent the correct authorization token. Then it will send the bank account channel to Alice's bank account to Alice. And after that, it will send the message success to the attacker, indicating that Alice authenticated herself correctly. Let's look at the branch where actually Alice sends the wrong token. In that case, the sneaky authorization process will send the message fail. And then also, in addition, it will send the message fail to the attacker. As you might have guessed, this amounts to an insecure program. It's a so-called indirect flow because now the attacker can learn whether the Alice sent a correct token or not. So here we assume an attacker model where the attacker can make observations of the messages that are being passed. And it also knows the code. So observing, for example, the message fail, the attacker knows that Alice authenticated herself not correctly. All right, so now that we've kind of set the stage and understand what the primary concerns are in information flow control, and in particular that there are two kinds of flows that we're after, direct and indirect, let's work out together a type system using possible worlds in order to control the flow of information. Okay, so let's first kind of develop together the main ideas. So let's target direct flows first. All right, so again, here we have our program, and I'm also basically having the two lines of code on the slide where where we send Bob's authorization process to Alice and Alice's authorization process to Bob. And let's remind ourselves that how did we define our security policies? Basically, we set up a security lattice. So we have the lattice where bank has top security and guest is bottom. And let's now try to somehow connect this idea of the security lattice and the policies that it imposes to our program. For this, we are going to introduce or kind of enrich our program with a security label that I refer to as maximal secrecy here, which basically indicates the security clearance of a process. All right. So what does that mean? The maximal secrecy defines what is the maximal level of knowledge a process is ever allowed to obtain. So given that we have this label now, we can basically assign a maximal secrecy level with each process that we have in our program. So obviously we assign the bank process the label bank, and Alice, we assign the label Alice. And consequently, we also assign all the processes that deal with Alice, so her authorization process and her bank account with the label Alice. We do the analogous thing with Bob and all the processes relating to Bob. Now that we have made this assignment, let's consider this insecure program again. well, provided that we somehow develop the type system in this way, now we basically have all the information at our hands, and we can clearly say that this line of code should not be permitted, because here we would allow Alice to obtain knowledge that is out of her realm according to the security lattice. In particular, Alice can only learn information of up to level Alice. And the same holds true for the second line of code. Again, here, this would be flagged because Bob is only allowed to acquire knowledge of at most level Bob. Okay, so it seems like somehow associating maximal secrecies with our processes is a way to go to prevent indirect direct flows. Well, I kind of already kind of foreshadowed that. So let's look at indirect flows next. Again, I'm remind you of our example program. So where we have replaced the Alice authorization process with a sneaky authorization process that is also connected to an intruder. And basically it will tell this intruder whether Alice authenticated herself correctly or not. Let me remind you again of the security lattice and our label. We are going to keep the maximal secrecy label. So it turns out to prevent indirect flows, the maximal secrecy level is not really sufficient to capture that, because it only tells us what is the security clearance of a process, but it doesn't tell us what is the momentary level of knowledge the process has acquired up to this point. Okay, so, and I'm also basically showing again on the slide the assignment of this max secrecy. All right. In order now, I wanted to point out I was ahead of my animations. So the only difference now is we choose the guessed maximal secrecy for the intruder. Okay, in order to somehow capture what is the knowledge that a process has learned up to that point in the program, we introduce an additional label that we are calling running secrecy. Okay, and the running secrecy really captures the highest level of knowledge obtained so far. All right, so let's look at our example program. At this point, where we receive an authorization token from Alice, the running secrecy of this process is raised to level Alice, because we've learned information from Alice, which means that the continuation of this program is going to run at running secrecy Alice. When you now consider the 2 sends to the attacker, which means that we would be sending to someone at level guest, we can obviously flag that code because we would leak information of level Alice to guest. Okay. So now we have basically the general ideas how to go about this, but we don't have a type system yet. And really, when it comes down to kind of designing a type system for a particular purpose, for a particular verifiable property, we somehow have to identify the invariants, the good invariants that have to hold for any program that executes. And when you take a step back, or maybe if you've already wondered, but maybe, maybe you were asking yourself, why did she draw those processes like a tree, essentially, right? And that's exactly what I get from intuitionism. And also what that kind of tells me is that the configuration of processes, or also like the heap of the program, is nicely aligned with the security lattice, just by virtue of how we spawn things and how the program evolves. So that kind of tells us that maybe that's a good idea. And what did I mean by saying that it nicely aligns with the security lattice? Well, what I meant is basically what it holds true for my configuration is that any child process has at most the knowledge of its parent. All right. So given that observation and a little bit of experience with playing with such systems, you kind of know that this is valuable and that's what is worth going after. All right. So let's start out by kind of distilling those high-level invariants that I want to hold true for my type system. And our invariant number one is that the process configuration should conform with the security lattice. Okay, now let's figure what are the other good properties that we want, and that really fall out naturally from how the intuitionistic program kind of arises and evolves. Well, clearly, it's kind of implicit, right? But how do the running secrecy and the max secrecy relate? Well, we said that the max secrecy should indicate the maximal security clearance or the security clearance of a process. And thus it indicates the maximal knowledge that a process can ever learn. So we clearly want it to be the case that the running secrecy should be capped by the maximal secrecy. So our type system has to ensure that that's the case. Okay, another important fact that we want to hold true for any well-typed program is that the running secrecy indeed soundly reflects the information learned so far. So what do we have to do for this? Well, whenever we receive, we have to make sure that the running secrecy of the recipient is at least the maximal secrecy of the sender. So that requires us to possibly bump up the running secrecy upon a receive in the typing rules. And on the other hand, for the send, we have to make sure that we not possibly leak information. So before a send, we have to check that the running secrecy of the sender is at most the maximal secrecy of the recipient. Okay, so those four invariants together really allow us to rule out the direct and indirect flows that we identified earlier. In particular, invariant 1 and 2 kind of targets direct flows, and the invariants 2, 3, and 4 indirect flows. So what we're going to do next is now really devise the typing judgment and the typing rules such that those invariants are enforced by typing. Okay, so for this, we are going to use this idea of possible worlds information flow control type system. I'm going to dive a little bit deeper now, so I'm kind of marking this with a star. So those people who are familiar with typing judgments are going to enjoy it. Others, I'll just rest assured that you know the most important ideas and just try to kind of tag along with me, all right? Okay, so the typing judgment that we typically use in a linear session type setting looks like that. And basically it reads, given the typing of channel variables in delta, process term P offers a session of type A along channel X. All right, so let me point out this delta is a linear context. So this means it does not enjoy weakening or contraction. And more intuitively, it means that it imposes ownership. So at the end of the day, it achieves the same thing as ownership type systems. All right, and let me also point out to you that this is really an intuitionistic sequence. So we have one thing on the right and we cannot swap sides. So we don't have dualization as we have in a classical linear logic setting. Okay, and the fact that this is an intuitionistic linear sequence means that I can type the configuration. A typed configuration essentially amounts to a directed tree, okay? And that's really important for the work that I'm showing here. Okay, so that's kind of what we start out with if we use an intuitionistic linear sequence for an session type system. But now we are going to augment this with possible worlds. And you might guess, we basically use it to kind of express the maximal and secrecy and the running secrecy. And we also have to throw in a security lattice, of course. All right, so let's do that. So that's the final judgment that we get. So here you can see the running secrecy. So we annotate the process term with its running secrecy. This here, in brackets, the D denotes the maximal secrecy. And you can see that I showed, it's basically part of the type. That's obvious to a client, whereas the running secrecy is internal to the process. And the max secrecy is kind of a sound upper bound. And then we type check relative to the security lattice psi. Okay, this together now means given the typing of channels in delta and security lattice psi, process P offers a session of type A and maximal secrecy D along channel X at running secrecy C. All right, so what we can do now is basically add the invariants 1 and 2, which is ensuring that the max secrecy, that the running secrecy is capped by the max secrecy and the max secrecy aligns with the security lattice. So we impose those invariants as presuppositions on the typing judgment. Well, what does that mean? It's similar, it's really analogous to an invariant-based verification methodology, if you're familiar with that, where you have this idea that on entry to a method, for example, you are allowed to assume the method if the methodology is sound, and you only have to establish the invariant at the exit of the method. In this setting means that if we presuppose those invariant on the typing judgment, it means we're allowed to assume the invariant holds for the conclusion, and we have to establish it for the premise. And keep in mind that we are in a sequence calculus, so we have like a bottom-up reading of the rules. Okay, these are the two invariants that we impose on the judgment as presuppositions. So here we say that for any channel Y of type B at maximal secrecy D prime in our context delta, it has to hold that the max secrecy D prime of that channel is at least as high as the max secrecy of the current process. So that really enforces this invariant that we saw earlier, that a child has at most the knowledge of its parent. And the second one is here we impose that a process cannot learn more secrets than it's licensed to. Okay, so let me briefly give you one typing rule. So that's for the internal choice. It's the right rule. We are in a sequence calculus, so we have right rule and left rules. Those of you who are familiar with natural deduction, the right rule is kind of analogous to the introductory rule in the natural deduction, and left rules with elimination rules. Modulo sum, of course, details. Well, okay, so what does this rule say? It basically says I'm a process that is sending along channel Y the label K, then continue with P, executing P, and I'm running at running secrecy C. And then above the line, the premise, we are typing the continuation P. All right, so we have to ensure that those presuppositions hold for that rule, and also the invariance regarding the kind of the interplay between the max secrecy and the running secrecy. All right, so let's look at the first presupposition. As I said, we are allowed to assume that this presupposition holds for the conclusion. So we know that it holds true for all the channels in delta. And we have to make sure that it also holds for the premise. Well, since it's the same delta, it just the accuracy holds true. So we don't have to add any additional premises in order to ensure that the presupposition is maintained. And so let's look at the second one, which indicates that the running secrecy is capped by the maximal secrecy. So by presupposition, we are allowed to assume that this holds for the conclusion, which means we know that C is less than D. And as you can see, because we just have sent something, so the running secrecy is the same. So it holds true just by knowing that it holds true for the conclusion. now we have to actually check what about the relationship between running secrecy and max secrecy, right? And we phrase them as specifically for the case of a receive or a send. Here we are dealing with a send. So we have to make sure that we're not possibly leaking any information. And we know by presupposition that our running secrecy is less than D. And so we know that, and also by kind of the invariant that is imposed on the entire tree structure, we know that we're not leaking any information because our parent will be at least at the same maximal secrecy. Okay, I think there was a question because something popped up.
Yeah, I was about to read out loud. I was
okay.
waiting.
No worries.
So is it a good time now? Can you read it?
Sure, absolutely. I cannot read it.
Okay,
it's just like the icon, chat icon has a red one.
So I will read Sanjeeva's Prasad question unless he wants to speak up. He's asking about the K belongs to L in the antecedent part of your rule. Does that mean that that all K such antecedent hold? Such antecedent.
Well, that would be the case for the left rule, because here we are in a positive connective, so we are making the choice. But for the left rules, you would have for all possible labels a premise.
Okay.
Okay. So if that's okay, then I think in interest of time, I also have worked out the left rule, but it's kind of, I've illustrated the main ideas. So I will actually just skip the left rule because I also want to talk about, have enough time for the logical relation.
Okay, so maybe I have another question about the rules.
Sure.
Does the lattice ever change? Is there a rule that makes any alteration in the lattice, or is it always fixed right from the beginning and you never change it?
That's a very nice question. Actually, the lattice is fixed. But okay, so I mentioned that I kind of like this idea of possible world type systems, and depending on your application, actually the lattice or order, usually it's like a partial order. You can actually populate it by the program. It really depends. So for example, in the deadlock freedom work, that's what we're doing. We're populating the order, we're creating it basically at runtime and also in the program text.
Okay.
Yeah.
So you cannot construct the order while working on the derivation. You have to first have it and then enforce it.
Right, because I just think so first, that's what we've seen so far. Like you define your security lattice up front for the application.
Yeah.
But it would be an interesting question. We've already thought like maybe at some point we want to see whether there are some applications where that might make sense. Whether it's feasible, I don't know. Okay. But for me, it's more like a question of the application domain, whether it makes sense or not. Yeah. In this domain, usually it's a fixed security lattice.
Sure, yeah, okay. But I was surprised that you would parameterize all your rules by this lattice. I think you could just get rid of it.
You can. I like to have everything explicit because we have like several premises that require that you can find the relationship in the lattice. Yeah. Okay.
Sanjeeva also added in the chat that following on my question, we should or could consider Meyer's decentralized label model. So I'm not familiar with it.
What was that? Sorry.
Meyer's decentralized label model.
Oh,
so
okay.
M-I-E-R.
Yeah. That would be like something to look into for me. So this is really like the first cut. Really getting the logical relation right for this kind of setting, and then various next steps that we can do. But thanks for the pointer.
Thank you.
Okay, all right. So let's briefly take stock. So essentially, what we have at this moment, if you believe me, that we can do this kind of things for all the rules. So then we have a flow-sensitive information flow control type system for message passing concurrency. you probably, if you've worked in this area already, you won't be surprised that type safety is straightforward because we just have a intuitionistic linear session type calculus. And so what I mean by type safety is basically protocol adherence, or also referred to as preservation or session fidelity, and progress, which is in this setting also guarantees deadlock freedom. Okay, so, but what we haven't done yet is we haven't shown that any well-typed program enjoys the property of non-interference. So in order to do this, to define non-interference and to prove it, we use a logical relation. So that's kind of the last part of my talk, what I want to spend some time on. But firstly, let us understand together really what non-interference is about. Earlier, I said that essentially it boils down to the fact that we do not want any attacker to be able to infer secret information just by making observations. And typically, this statement is parameterized in the secrecy level of the attacker. So an attacker cannot just see any information, but any secret information that is above the attacker's pay grade, the attacker is not allowed to see. Okay, that's the basic assumption of the model. All right. So what does that now mean? How, in such a setting, how can an attacker even make any, basically observe or infer any secret information? Well, this is possible because we have branching typically in our programs. In this setting, branching arises from internal and external choice. So inference for an attacker is possible if it can observe different messages along the same channel in 2 runs of the same program that branches on high security information. So actually, we have seen such an example. That was exactly the indirect flow, right? So this is the code snippet that we looked at earlier. And let's now consider 2 runs of this program, 2 possible runs of this program together. On the left, I think I'm showing, yeah, exactly. I'm showing on the left basically the successful run where Alice authenticates herself successfully, and on the right where she authenticates herself incorrectly. And you, by the way, can also see it because on the left, Alice has access to her bank account already. The channel has moved up to her. Okay, so that's precisely this scenario where now in the authorization, in the sneaky authorization process, we're branching on a high security information, which is the authorization token that is sent by Alice. And then we're sending a message to the attacker, okay? And this way, the attacker is allowed to see messages that are being sent to it. And just by observing those messages, it now can see that, can infer whether Alice authenticated herself correctly or not. All right. Okay, so what does that mean for us? Essentially, at the end of the day, non-interference can be stated as an equivalent statement of the program with itself up to the secrecy level of the observer, right? So the program, we have to show that the program is 2 runs of the program, so to speak, are identical unless they concern parts that are above the pay grade of the attacker. All right, and there are different ways to achieve that. Typically in a PyCalculus setting, people have used bisimulations or barbed congruencies, and we are using a logical relation for this. That was just a choice. We were both very curious using it, and we love logical relations. So it was an interesting endeavor. Okay, so again, I would like to develop the high-level ideas, the main ideas underlying this logical relation. So the logical relation argument at its bare bone typically is that for this non-interference setting, or just in general, that basically two things are related if there are given related substitutions, right? So that's really like the extensionality argument that is inherent to a logical relation. So, well, in a functional setting or imperative setting, it means like we can observe input and output, right? So if we are given related, or we can assume related inputs, we have to show that the outputs are related that we're producing. In a message passing setting, the things are slightly different because our programs do not yield the result and then end, right? They might terminate if you terminate the process, but that doesn't have to be the case. But otherwise, the processes are kind of continuously there, ready to interact with you, especially once you throw in recursion. Okay, so in our setting, relatedness really means sending the same messages. Okay, so again, let's go back to our example and allow me to illustrate this. So here we have our banking example, and we want to, at the end of the day, we want to say, well, okay, those two runs, D1 and D2 of our banking example program, they have to be related. And the substitution here is basically our attacker program that interacts with our banking application. And so I'm referring here it to as by C1 and C2 to denote them as substitutions. And what does relatedness now mean? It means that the programs D1 and D2 are going to send the same messages in both runs, assuming that they're also receiving the same messages from the substitution in both runs. Okay, so that's exactly the same idea. Two program runs must be related if given related substitutions. So in this setting, it really means that if C1 and C2 send the same messages, then D1 and D2 send the same messages too. And we kind of capture this with C1, D1, and so C1 composed with D1, C2 composed with D2 are in the value interpretation of the logical relation. So that's the basic argument. And then of course, we have to work that out. Okay, so that's the main idea. And I'm going to take the opportunity to again dive a little bit deeper, but as long as everyone's with me up to here, so I'm really proud. And for anything more detail, just bear with me, okay?
Maybe I have a quick question before you answer. So I'm guessing from the perspective of your type system, it is not possible that the person with maximum rights at the top of the lattice is denied anything. They are capable of doing everything.
Right.
Okay. I guess that's it. So like the type system enforces that if you have superior rights, then you really do have superior rights from the from the agent perspective. Okay.
Right. And typically what that also means is because of intuitionistic setting, the main process like that spawns everything else has typically top secrecy.
Yeah, okay.
And right, but it typically starts at the lowest runner secrecy possible.
Yeah, okay.
So you have like a pattern which is really in line how things spawn. When you have a linear session type system, you start out with the main process, it spawns forks of other processes, and then basic computation happen by growing the tree, and then eventually the tree grows back, and until you're back with the main process. Okay, all right. Okay, for those of you who are familiar with logical relations, will see that I previously, when we went here, when I basically showed you this, you would think that I lied or I simplified, because what's the key thing of a logical relation, right? It's indexed by it basically is well founded in the type structure, okay? So somehow I kind of didn't show you how we index this value interpretation. Okay, so let's work it out together. So there's a little bit more space here now because I'm going to fill in more stuff, right? So I'm saying now I have D1 and D2, and has to be in a value interpretation of this logical relation, but it requires substitutions. Okay, so let's look at the typing of such an open configuration D1 and D2. So it says that D1 expects channels that are in delta. So we have channel variables in delta on the left, and it's going to offer us a session along channel X of type A, and the same for T2. So what does that mean, really? We can see that a program, an open program here in our setting, so an open configuration, has channels along which it wants to interact with the external world, and it basically defines what are its expectations in terms of types along that interface with its external world, and that's here in green. Okay, so that means once we state the logical relation, we have to consider possible substitutions. So we have in our intuitionistic setting, because of the tree structure for an entire program, we have substitutions from the bottom, which are C1, C2, that really provide processes and actual channels at runtime for the variables in delta. And we also have a substitution on the top, which I refer to as F1 and F2, with the typings that I show here on the slide. Okay, so putting this all together, we now can say that the value interpretation of our logical relation is that D1 composed with C1 and F1 and D2 composed with C2 and F2 are at the value interpretation at the interface delta turnstile X colon A, right? So here we're basically saying that we index the logical relation with the types of the interface along which the program, the open program that we're looking at, interacts with the outside world and along which we can make observations. I point out that here we have magically defined those parts D1, D2, C1, F1, and F1 and F2 in a way that everything that is here green is really observable to the observer. And that's a definition, which means if it's not the case, we just move subtrees around. And for that, I refer you to the technical report. All right, so very briefly, I said this is the value. So we kind of require that those two configurations with substitutions are in the value interpretation of this type at this interface. Well, you might wonder, or you might know that typically we also have to account for an evaluation interpretation, right? Because the program can stack. And you might wonder, what does it really mean for this to be at a value, right? Basically, what I'm saying is I consider those two close programs to be a value. Well, as I pointed out, in a functional imperative setting, a value is really like the program evaluates the value and then it's done, right? In our setting, that doesn't really hold true. So what is a value in this setting? Well, we define it as a so-called poised configuration. So D1 and T2 are poised if they cannot make any internal transitions, but really only can interact with the outside world along the green channels. That's a poised configuration or a value in our setting, which means by virtue of those two configurations being in the value interpretation, it means there has to be somewhere a message which is kind of waiting to be sent along an observable channel. So I'm denoting here this with a red dot. And so what we then do is we allow this message to be pushed into the substitution. And then we basically say that the former is at the value interpretation if the post state is at the evaluation interpretation. Okay. And then we allow those configurations to make internal steps. So each of the parts, so the red part, the blue part, or yellow part, they are allowed to make internal transitions until they're again at the value interpretation. All right. So that's as much I want to say and can say given the time. So, but of course, you might be wondering, what did we prove at the end of the day? Well, we proved type safety, of course, of the system. And then we proved the main theorem, or theorem one, which is the non-interference theorem, which really says that the program is related to itself up to the sequence of the observer. And this triple equality sign is defined in terms of the logical relation. As always in this development, really like the key workhorse of the proof is done using the fundamental theorem, which allows us to relate two possibly different runs of the program. Because as we know, once the program starts to evaluate, different choices can be made, branches can be taken on high secrecy information. If it's safe, then anyway, the programs might actually run different code. Okay, and in addition, we've also proved an adequacy theorem, which is basically yields a trace-based definition of related program runs. And again, this is really only a spoiler to the paper. There's lots of details, but I think hopefully if you're interested in that, I set you up to understand that paper. So let me summarize. In summary, I've shown you how to develop an information flow control system for intuitionistic linear session types. And I hope gave you a good intuition for what you can achieve with those possible worlds. And it's really like the possible worlds somehow stratify the configuration to align with the security layers. And that's also, there are similarities to cryptological relations or possible worlds models, to stratify the heap. So that's quite interesting, actually, even though the details are very much different. But I think at a high level, those things are nicely related, and that's very intriguing. Let me also emphasize that the logical relation that we developed here is really a generalization of existing logical relations. There have only been 3 papers on logical relation for session types, and they all focus either on a termination argument or parametricity. But for dealing with non-interference, we had to, in particular, use open configurations. In terms of future work, something that we're working on right now for Sunny and I is introducing recursion. And then down the road, we would like to combine this work, or basically adopt it for shared session types where we have non-determinism, and yeah, it's a whole other category. Okay, so that's it. Thank you very much for your attention.
Okay, Stephanie, thank you so much for building your talk in such a principled way with the stars and indication of where the difficulty was.
Oh, good, good. I'm glad.
That is extremely appreciated. Andrew Wagner had a question in the chat about your value relation.
Okay.
He was wondering if all of C, D, and F were poised, or only, I forgot which one, only I get the middle one. Probably.
Yeah. That was D. Yeah,
D.
no, to be in a value interpretation, they all have to be individually poised.
Okay.
It's only once, they all have to be individually poised, and then when it's in the evaluation interpretation, they can individually step.
Okay. So I'm assuming this answer.
Right. And also I should point out, I didn't really make this, I didn't say that, but we developed it for an asynchronous semantics of the calculus. And first we started with a synchronous one, but then it turned out by being asynchronous, we actually can be more permissive. So we have to reject less programs because it essentially allows you to it allows you one run to catch up if it's not relevant for security.
And okay, maybe I had a question, but it's about future extension, so it's always a kind of tricky question. But when you're saying recursion, do you mean because in process calculi there's always the question: do you want recursion, iteration, constant that allow you to trigger the recursion, etc.? Do you have a I'm wondering on session types, what is the most convenient way of doing that? I guess replication is kind of always the main target. Is this what you have in mind?
No, so yeah, we could use like when you like replication in a PyCalculus is like linear band, right? But no, that's not what we had in mind. But we really wanted to have like like a letrec, you know.
Okay.
So right. But for this in our setting, it's kind of interesting because like in a functional setting, if you add, you can, for example, just add recursion to the term level. Mm-hmm. But in our setting, we really need to have recursive types, even if we allow like recursion on the term level. So what we are doing right now is extending the formalization to support process definitions, so top level definitions. Okay. So then in the body of a process, you can call yourself. And that already kind of, you know, then you have to account for simultaneous substitutions and so on. And we want then to make the process definitions polymorphic in the security levels. So this is all straightforward in principle, but when you work it out formally, it's still quite intricate. And then the next step after that is to add recursive types. But then we have to, our logical relation, we probably have to use some step indexing or so, because the logical relation won't be well-founded anymore. So yeah, that's these are the things that we're working on right now.
Okay.
I've actually stopped screen sharing, so I can see the chat now too. But okay. I can also go back to slides if people have questions.
Okay, okay. And so on the label, you only add the secrecy level, is that correct?
So let me maybe screen share and then look at the typing judgment. Okay.
I kind of need that step when you.
So here you mean, because I have here the maximal secrecy. That's basically part of the interface, if you want, or the signature. And then here at the term level, I have the running secrecy. So you need both. The entire system really needs both. And that allows the system to be flow sensitive. I can also show the, yeah, here I also have the left rule, by the way, which is a bit more involved. Maybe that's more interesting because here I'm actually doing a join.
Yeah, that makes sense.
Yeah, because, so here we have received some information. So we are receiving from the left. So we have, in our context, we have an internal choice. And we know that whatever we will receive from it is at most at level D prime. And we are currently running at running secrecy C1, which is again capped by D. So in the continuation, we have to account for the possibility that we learned information up to level D prime. So we are continuing with C2, which is the join of D prime and C1.
Do you really mean continuation in the sense of continuation passing?
No, I don't think so. We usually refer to as the continuation. So it's just the code that happens after the synchronization.
Okay. So in the process calculus sense of continuation, not in the Griffin interpretation of continuations.
Yes, that's correct.
Okay. So is it correct to understand this language as a deterministic sequential language?
Yes, it's correct.
Okay.
So it's
that's
parallel,
why I was.
But
yeah, I'm curious where it's parallel in the sense that the lambda calculus is parallel, has parallelism in it.
Yeah.
Or admits parallelism. Okay.
Okay, that's a very good question, because we are in the linear fragment here. It is deterministic in a sense that you cannot observe there's no observable non-determinism. So there is a confluence result, in this calculus. And actually our proof relies on that. We have like forward and backward closure, and we prove a diamond property. Okay, That being said, in my last slide, I am saying here that we want to integrate it with manifest sharing. So I'm alluding to some prior work that's a work by Frank Penning and me, was presented at ICFP 2017, where we kind of complement linear session types with shared session types. So we have an adjoint formulation where kind of linear and shared sessions can, or processes can coexist. So in this setting, we are no longer deterministic. We do have observable non-determinism.
And in that setting, would you be able to just compare a process with itself, you know, the sort of self-composition idea, or do you have to do something different? I was intrigued by you saying that they send the same messages. I would have thought you would have said they send messages that are indistinguishable to an observer with a particular security level.
Well, okay, so my statement, if you look at the paper, so for example, when we have tensor and lolly, right? So my statement was sloppy. So when it's tensor and lolly, we're actually receiving not just the label, but we're receiving an entire tree, process tree. And that there we require that the trees that we're receiving are again related by the logical relation. So they don't have to be exactly the same. So that would be awful if we were to do that. We would kind of, you know, cut the wings of the logical relation. So yeah. So yeah, that's a nice question. That being said, as I said, at some point down the road, we want to integrate it with manifest sharing, which really requires us to deal with this non-determinism. And I don't know yet how to do that.
Yeah, non-determinism and, you know, recursion, which is not merely replication, tend to go terribly together. You lose all your confluence, right?
Yeah, we don't have that anymore.
Yeah, I was just wondering, I was a little curious about the comma in your plus operator, the circle plus operator. Again, you were saying success and fail. Could the, if you weren't in a deterministic setting, would you be able to, you know, your example of auth, AUTH, so you have a success. So would you be able to, if the observer was able to see both, would they be able to distinguish processes with which were branching on a high condition?
If they were able to see
both success and failure.
Yes. So the exactly. So that example is not safe, right? Because exactly. So it would not pass the logical relation.
Okay.
The logical relation would require that we can only send the same messages. So in both branches, we would have to say hello or whatever.
If you had, like in the PyCalculus, the ability to generate names, then you might be able to weaken that statement from same messages to indistinguishable ones, because I don't know if N1 got generated or N2 got generated. I wouldn't be any, the observer wouldn't be any the wiser.
So when you say, so we have we can spawn processes, so that creates new channels, which are names in the PyCalculus. And that is okay, but the logical relation, so okay, so we basically kind of the interface with the outside world, or let me go to this picture here. So the interface with the outside world are really those green channels. As a matter of fact, in the logical relation, we only have the code of those two open configurations, so D1 and D2. But the substitutions are just like imaginary, right? But we only know that those substitutions are kind of adhere to the logical relation. So they're going to send us the same, as in the sense that you know, it's like the same. For this, we really have to look in the logical relation, right? But they're basically sending us the same messages, or let me say the substitution are in the logical relation, okay? So in the proof of the main theorem, the fundamental theorem, we have to strengthen the inductive hypothesis that we get, because it's actually quite beautiful. I hope I can convey that, but essentially, it's another way of stating what does it mean to be secure, and when do we possibly leak information? So once we have, so let's imagine we start out kind of with the program and we observe 2 runs. So at the beginning, they're exactly running the same code, right? And once they branch on high secrecy information, they actually might diverge in the code that they're running.
Right.
And when it's safe, that different code will never trigger a message that will be sent over that green interface.
Right.
And so we're basically in the main theorem, we have to strengthen the inductive hypothesis that those nodes that are possibly affect the green interface, we always have to assert that they're running the same code. So, yeah, okay. Thanks for your questions. I'm very impressed.
I mean, it's about 32 years ago that I did this stuff with higher order process calculi, so in my thesis. So it's old stuff for me, in a sense. I'm just trying to also understand when you say the intuitionistic world as opposed to the classical world will allows you to look at these as trees. So that's something which is intriguing, that you can always view the execution as moving things down in the tree, and that's quite interesting. It
is interesting. Let me be precise here. It's really the directed tree, because classically you also get like in Wadler's system, for example, ICFP 2012, which is a classically linear session type language.
Right.
That has like the standard cut. You don't have a multi-cut or anything like that. In that system, you also get a well-typed configuration forms a tree, but it's undirected. There's no designated route. And that's exactly what you get from dualization, because you can basically get your graph, right? It's acyclic. It's an acyclic graph. I'd like to phrase it that way. And any node you can kind of pick up and, dangling the rest from it, and you get one possible tree. But in intuitionism, you don't have that. And that's very nice if you want to impose invariants like the ones I do. Just by virtue that it's a directed tree.
Yeah, I liked your comment at the end that you said that the asynchronous one gives you greater leeway in interpreting things, which is interesting because in all this work, when concurrency was linear logic was being seen as an answer to concurrency, and Phil never is able to adequately answer this one. The session types are imposing much more order than the sequent calculus, even the sequent calculus allows you, because sequent calculus allows you to commute rules pretty freely in the proof trees, whereas the session types are much more structured. So they're actually following a particular evaluation strategy. And the asynchronous one just sort of says it's not all that strict. Whereas the traditional pi calculus that David Walker and Robin Milner had much more sequentiality to it.
Right. Yeah. It's actually interesting that you know, that to my understanding, at least the original work was for a synchronous setting. But when you think about at least from my point of view, the asynchronous is much more general, and you can always get synchrony via an acknowledgement channel. So
yeah. That was an old trick we all used.
Yeah.
Coding one in the other and coding the higher order in lower order ones. Yeah. So. But that's exactly the CPS translation, funnily enough.
Yeah.
So does this sort of tie in very well with the work that Myers and Steve Dankiewicz did about information flow and linear continuations?
I think so, but I also have to admit that I have to revisit again related work, because it's the information flow control literature is enormous. And I'm not sure whether you can relate to that, but I feel like you start reading papers and you kind of understand what's going on, but really you understand only once you start working on it.
Absolutely.
And then I feel like, no, I really understand. So I just said to Farsani, we have to go back and reread those papers. And also sometimes I like to not be too, you know, I'd like to keep my mind free to some extent so that I'm not biased towards a specific solution. So I want to understand the problem, what it's about. And then I just want to start working on it and discover myself. So.
Right. Thanks. This is really interesting.
Thank you so much.
It's come out in Lix this year. Yes.
Yeah.
Okay, great. Is there a longer version on?
Yes, there's on Archive. Yeah, I'm linking to it from my website, and I have to say that I think if you are an Adobe Acrobat user, which I hope you're not, I think the PDF that I currently link to from my website cannot properly be displayed by the Adobe. But it can be, we just noticed it then later on because someone told us. So because there was a conversion problem, I made the figures using Keynote, and it doesn't produce a PDF that can be read by Adobe. So, and both Apple and Adobe were pointing the fingers at each other.
So does it correctly display on preview?
Yes, it does.
Okay.
Preview, Evans, Skim, I use Skim, does all properly work.
Okay. Thanks very much. This was very interesting.
Thank you so much. Thank you.
Okay, well, thank you so much. And thanks, Sanjeeva, for the very interesting discussion.
Thanks.
Yeah.
I did not see any question raised on the chat. But
we still have some people tagging along, so that's great. Some people stuck around, so that's great.
Okay, well, thanks everybody for joining. I wish you all a very pleasant rest of the day, a nice weekend, longer weekend maybe.
Yeah,
and,
even, yeah.
Thanks again so much, Stephanie, for accepting my invitation.
Okay, thank you so much.
Bye-bye.
Bye-bye.
Bye.